Hi, everyone. We'll give it about a minute or two and then get started. Thank you. Well, welcome. And this is one of our special technical series, Heat Pumps 201. And we will be recording the presentation as well as sending out a PDF of the presentation. And I want to make a note that AIA members need to be logged in for 50 minutes to receive credit. And we will be putting if you are not an AIA member, you can actually request a certificate, and I will be putting in a link to request that. And there is a $10 processing fee for a certificate for this. And I am Jan Culbertson with the Ann Arbor-Washtenaw 2030 District, and I'd like to turn it over to Karen Neubauer, who will be introducing our speaker.
Thanks, Jan. Hi, everybody. I am Karen Neubauer. I'm an architect at Quinn Evans, and I am the AIA Huron Valley Continuing Education Director. So if you do have any issues or questions about your continuing ed credits, feel free to reach out to me. I'm going to go ahead and introduce our guest today. We have Zach Kozmal, who is an energy engineer with Energy Science. Zach is a dedicated engineer focusing on developing his analytical, technical, and leadership skills. Zach has a Bachelor's of Science in Mechanical Engineering from Oakland University. He also has a large base of knowledge and is passionate about energy efficiency and decarbonization. Zach's aptitude for time management and quick learning ability have produced unique opportunities throughout his educational and professional careers. These experiences have inspired Zach to continuously explore, learn, and improve on the complex concepts of engineering. He has worked on projects that include identifying and quantifying energy efficiency opportunities for industrial facilities, performing energy and economic assessments, and collaborating with customers to implement efficiency improvements. With that, I will cede the floor to Zach and let him get started on his presentation.
Thank you, Karen, for the wonderful introduction. And good afternoon, everyone. Thank you for joining us for Heat Pumps 201 today. Hope you're all staying cool and hydrated out there. I know we're all going through a bit of a heat wave here, so make sure you're drinking your water. And also thank you to the Washtenaw Ann Arbor 2030 District for providing this awesome platform to share knowledge and experiences. And Energy Sciences really appreciates this opportunity to share our knowledge about heat pumps. So we'll get started. So today's agenda, we'll be talking about different types of heat pumps, heat pump efficiency basics, how to compare different heat pump options, and then also the leading manufacturers per application, and process for equipment replacement with regard to heat pumps. So we'll start with different types of heat pumps. The two main types of heat pumps are air source heat pumps and water source heat pumps. An air source heat pump is a device that transfers heat between the outdoor air and indoor space to provide heating and or cooling. Some examples of an air source heat pump might include a split system or a mini split heat pump, packaged rooftop heat pumps, dual fuel heat pumps, and cold climate heat pumps. So all those types typically fall under your air source heat pump. Another type would be a water source heat pump, in which a device that transfers heat between water and an indoor space to provide heating and cooling. So with water source heat pumps, they can be utilized in several applications. You can use pond or lake water. You can also use groundwater or well water for that heat transfer mechanism, in which the heat exchange occurs with the water instead of the ground for a ground source heat pump. And for cold climate applications, the piping is typically placed at a minimum of 8 feet under the surface of the water just to prevent freezing in that system. So with water source heat pumps, you can have two different types of loops. So you can have an open loop system or a closed loop system. In an open loop system, the pressure in the system varies depending on the depth of the water source and the flow rate required to pump that water. So the system must overcome that static lift to draw that water from a well or groundwater or pond. Um, and that may increase the pump energy demand. So to summarize, an open loop system must manage fluctuating pressures from water extraction and discharge, whether that be from a pond, well, or groundwater source. In a closed loop system, you have a constant pressure within that system, which is maintained within a sealed circuit of pipes. The water is typically a water antifreeze solution to reduce any freezing in that system. So in summary, a closed loop system maintains a stable internal pressure, and it requires less pump energy by recirculating that water antifreeze solution. So another version of a water source heat pump may be a ground source heat pump. And you can see there in figure 2, that is an example of a ground source heat pump in which the piping is laid horizontally in that figure. You can have two types of ground source heat pumps. You can have horizontal, which as I said is shown in figure 2, in which the piping is laid horizontally at a minimum depth of 4 feet deep. Can vary depending on the application. The other option would be vertical piping, in which U-shaped piping is laid at depths between 100 to 400 feet, depending on the application, and that pipe system has the vertical pipes. In general, heat pump systems can be utilized across many industries and applications to transfer heat for the purpose of heating, cooling, and waste heat recovery. But typically their system components remain the same. So we have the key components listed here. You have your evaporator and condenser, your refrigerant coils, compressor, expansion valve, reversing valve, refrigerant, and your fans and motors. So if we look at figure 1, you can see that the outdoor coil, in this case the evaporator coil, because it is a heating cycle, and I'll explain that further in a little bit. But the outdoor coil in this case absorbs heat from the outside air using that refrigerant. We also have a compressor moving to the right. The compressor increases the pressure and temperature of that refrigerant, making it capable of releasing that heat indoors. And then next you have the indoor coil, which transfers heat to the indoor air, warming that space during the heating cycle. You also have the expansion valve, which regulates the refrigerant flow and the pressure to ensure efficient operation. You also have a reversing valve, which allows the heat pump to switch between heating and cooling modes and reverse that flow of the refrigerant within the cycle. You also have fans, which helps move air across the coils and facilitates heat exchange. And lastly, the refrigerant, which is the fluid that cycles between evaporation and condensation, so liquid and gas, and it carries that heat in the process. So in this figure, we have examples of a packaged rooftop heat pump along with a split system heat pump, just to give you an idea of how these two systems may look in the real world. Both of these examples are air source heat pumps. So on the left-hand side, you have your packaged rooftop heat pump. This would look typically like your traditional rooftop unit. It's just a little larger typically because there's a few more components within that system. And then on the right-hand side is your split system heat pump, which that component on the rooftop there is a condensing unit or evaporated unit, depending on the heating or cooling cycle. But that looks very similar to your residential condensing unit that you may find outside of your home. And that refrigerant loop just connects to the coil that is within that air handler inside of the building. So these are just two examples of air source heat pumps. Moving on, so this is an example of a water source heat pump in which a cooling tower and a boiler are utilized for supplemental heating and cooling. So I didn't mention this previously, but with water source heat pumps, you can tie in a cooling tower or a chiller and a boiler to do that supplemental heating and cooling when needed. So this setup, it allows for different zones in a building to simultaneously heat and cool. With the water loop, you can see the water loop is just below that roof level, the horizontal blue piping. That's acting as your thermal exchange medium. So if a space is calling for heating, it'll pull heat from a space that may be calling for cooling, and it can distribute that heat to the area that's requiring that heat. So the boiler and chiller or cooling tower in this case are like the system's backup dancers, if you will. They step in only when the internal heat exchange between zones isn't enough to keep the loop in balance. Okay. It should also be noted boilers, cooling towers, chillers, they should be included when you're doing your energy modeling to predict the system performance. Um, and these additions may impact the life cycle costs of your system as well, which could deem this option too expensive in some cases. But if you're just looking for a very reliable system, this might come with a higher price tag, but you'll get really good reliability out of it. So moving on. So I just want to touch on the process of heat transfer a little bit. So the figure in the right is the refrigerant flow in a heat pump. This is the cooling cycle specifically. So it's a reverse flow of that refrigerant from that first figure on the first slide. So if you start at 1 at the compressor, the refrigerant enters the compressor as a cool, low pressure gas or vapor, and it leaves as a hot, high pressure gas. And so as that refrigerant passes through the outdoor coil, in this case, the condenser coil in cooling mode, the heat from the refrigerant is released into the outside air via the outdoor fan, and this process cools the refrigerant and it changes state from a gas to a liquid. So next, we move to step 3, our expansion device. So this high pressure, high temperature liquid refrigerant leaves that outdoor coil, and the temperature and pressure is further decreased as it passes through that thermal expansion valve or expansion device. Interchangeable wording there. And then we move on to the inside coil, which in this case in cooling mode will be our evaporator coil. That liquid refrigerant evaporates while it absorbs heat from that return air in your indoor system. Simultaneously, moisture can also be removed from the indoor air at this step. That's that condensation that drips into your drain pan and probably leads to a drain near your HVAC equipment. And lastly, the refrigerant leaves that indoor coil as a gas and arrives back at the compressor to repeat that cycle. So again, this is a cooling cycle. If we were in heating mode, this cycle would just reverse itself, in which case that inside coil would become your condensing coil, and the outdoor coil would become your evaporator coil. So it can get a little confusing, especially if you're thinking about an AC unit specifically. We always call those outdoor units for your residential AC units. We call those condensing units, but that verbiage can change depending on heating or cooling cycle in a heat pump. So, moving on to heat pump applications. So there's many applications for heat pumps. Residential heating and cooling is maybe the most common. Some examples would be a split system heat pump, as I mentioned, similar to that your home's condensing unit. Or you could have a mini split heat pump, which looks similar to a mini split AC unit. Those are commonly found in warmer climates or hotels. You can see them mounted up on the wall. We also have commercial building applications. So there's a wide variety of heat pump types. That's why we're all here today, I believe, to discuss all of those commercial heat pump applications. We'll touch on the main applications today. And I'll touch on some specific commercial building heat pump applications later on in this presentation. We also have industrial processes. Typically, this will be for waste heat recovery within a manufacturing process. Um, I could spend a whole hour talking to you about all the various applications of industrial heat pumps, but to give you a general idea, majority of these heat pumps are utilized to recover waste heat from a manufacturing process. That recovered heat is then reused as heating energy elsewhere, whether that be for heating an adjacent office space or to preheat components within that manufacturing process. We also have domestic hot water heating applications. This can be utilized in commercial and residential domestic hot water heating. So pretty cool application there. We also have swimming pools. You can have a heat pump heater on your swimming pool. And we also have district heating systems. District heating systems are quite common in northern regions of Europe, places like Denmark, Sweden, Finland. These types of systems are a cornerstone of their energy infrastructure. And the utilization of these large-scale heat pumps within those systems allows for further decarbonization and increased energy efficiency. So if you're interested to go down a bit of a YouTube wormhole, district heating systems in Europe are quite interesting. So moving on to heat pump efficiency basics. So how is a heat pump efficiency determined? There's several metrics. These are the four main metrics here. The first is the coefficient of performance, or COP. This is the ratio of heat pump heat output to the equivalent electric energy input. So the coefficient of performance is a unitless value. Therefore, a unit conversion is typically required to calculate this value. A higher COP implies that the unit has a higher efficiency. And the simplest example of COP would be an electric coil or an electric heater, which has an efficiency of 100%, meaning your input energy equals your output energy. And that is a COP of 1, to kind of set your baseline there. So just to give you some ranges of COPs for different types of heat pumps, an air source heat pump generally varies between 2.5 to 4 on the COP. A 4 COP, just a reminder, would be 1 unit of input energy equals 4 units of output energy. So you can see how that efficiency is extremely impactful, and we'll get into kind of why that is a little bit down the road. Ground source heat pumps, those range between 3 to 5, and then water source heat pumps range from 3 to 5.5. The next is an energy efficiency ratio, or EER. So this is a measure of the cooling efficiency of a heat pump, expressed as the cooling heat output in BTUs per hour, divided by the electrical power input in watts. Energy efficiency ratio is not a unitless value. Rather, it is the BTUs per watt hour for a heat pump. Next, we have heating seasonal performance factor, or HSPF. This is a measure of the overall heating efficiency of a heat pump over a season. This is expressed by the heat produced during that season in BTUs, divided by the electrical power consumed during that period in kilowatt hours. HSPF is often regarded as the average COP over an entire heating season. So for example, an HSPF of about 6.8 would be comparable to an average COP of 2, okay? And lastly, we have the seasonal energy efficiency ratio, or SEER. This is a measure of the seasonal cooling efficiency of a heat pump expressed as the total cooling output in BTUs over a cooling season divided by the total electrical energy input during that period in kilowatt hours. So to determine SEER, manufacturers typically will test the equipment at various loads. For example, full load, 50% load, 25% load, etc. And they weigh those results based on typical usage patterns. And interestingly enough, SEER was recently replaced with SEER 2, not to make things more complicated, But SEER 2 is now the official standard of efficiency ratings since 2023. And the key difference is that SEER 2 accounts for more real world conditions, such as ductwork resistance and static pressure within that system. So SEER 2 is typically a bit lower than your original SEER. So for example, a 14 SEER unit may be rated around 13.4 for SEER 2 rating. Okay. And we will expand on these efficiency metrics a little later on in the presentation, and I'll touch on how to compare them and when each efficiency metric is most useful. Okay. So, what factors influence heat pump efficiency? One of the largest and key drivers of this is your outside air temperature. Okay. So heat pumps operate by transferring heat rather than generating it. And I just touched on how those COP values can be much higher than electrical resistance, for example. And that is the reason right there. Heat pumps do not generate heat, they transfer it. Okay. And whether that medium be your outside air for an air source heat pump or groundwater for a water source heat pump, that purpose is transferring that heat rather than generating it. So heat pump efficiency decreases as the outside air temperature decreases as well. This is because there's less heat available to extract from the air. Okay. So if we turn our attention to the figure at the right, this is a typical heat pump operation with supplemental heating. And so you can see that the heating load, as shown by the green triangle, the heating load is met by only the heat pump until that outside air temperature drops below 15 degrees Fahrenheit. Okay. And at that point, the heating load requires supplemental heating from the boiler. So an example of supplemental heating from a boiler, if you have large office windows in your facility, you may have a perimeter heating loop. This could be one example of supplemental heating. Another could be heating hot water coils within your duct system that only fire on during these supplemental heating periods. Okay. And so as you can see, as the outside air temperature further decreases, the boiler's supplemental load increases. And you can see that orange triangle, which is growing in size as it moves farther right. Now, eventually, that boiler will take on full load at 0 degrees Fahrenheit and lower, and the heat pump will turn off, and that boiler will take the full load, as shown by the red section in the figure. So this is a representative example of how a heat pump may interact with other heating and or cooling systems within a facility, whether that be a boiler, a furnace, a chiller, cooling tower, etc. It should also be noted that the turnover temperature or the outside air temperature in which the heat pump cannot handle the heating load on its own. That turnover temperature will depend on the system's design, okay? It's not always going to be 50 degrees Fahrenheit or 0 degrees Fahrenheit. It'll depend on that design, and it may vary depending on the specific application and heat pump equipment type, okay? So, what other factors influence heat pump efficiency? A defrost cycle is one big one as well. So in colder climates, we're in a colder climate, frost can form on the outdoor coil of an air source heat pump, as shown in figure 7 here. So frequent or inefficient defrost cycles will have a very negative impact on your unit's efficiency. So I'll go through the defrosting steps quickly. So first, your heat pump has sensors that monitor and detect the frost on the outdoor coil. That heat pump will temporarily reverse operation. In other words, it'll transfer into cooling mode, and it'll send warm refrigerant through that outdoor coil to start melting that defrost, or melting the frost, sorry. So some heat pumps may stop the outdoor fan to concentrate the heat transfer in the coil to expedite defrosting. And once that ice is melted, the heat pump will automatically reverse its operation back into heating mode and resume normal operation. So if needed, some heat pumps may utilize supplemental heating, i.e. a boiler or a furnace, to keep the indoor conditions stable during that defrost cycle. So it should be noted that heat pumps are typically designed to operate with a longer cycle time than a typical traditional HVAC system. So with that said, if an oversized heat pump is installed, then it'll likely operate on shorter cycle times. This will allow for the occurrence of frosting on that outdoor coil more frequently. So you kind of want to avoid that. In addition, short cycling causes excessive wear and tear on components, especially heat pumps. Things like the compressor will bang on and off repeatedly, which is just not good for the equipment. And frequent reversing from heating to cooling cycles will also lead to excessive wear and tear on components like that reversing valve. Okay. And lastly, one of the most common examples of supplemental heating in heat pumps is that electric resistance heat, which, as previously learned, has a COP of around 1, well, exactly 1, I should say. And it's not in the range of 3 to 5, like some of your heat pump options. So that supplemental heating should be used only for emergencies or times where that turnover temperature requires supplemental heating. Okay. So we'll touch on a few more factors that influence heat pump efficiency. The first is your building envelope. So a properly sealed and insulated building envelope is critical for proper operation of any heat pump. Um, if you don't have a properly sealed building, you may be conditioning this air, whether it be for cooling or heating. And if that air just excessively leaves the building, people like to say, don't want to cool the outside air, you don't want to air condition that outside air during hot summer days. So that insulation, building envelope, very critical. In addition, system sizing and design is also very important. A properly sized heat pump for the climate that it is operating in is critical for optimal performance. So an undersized piece of equipment may struggle to meet that heating or cooling demand, whereas oversized equipment, as we just mentioned, may short cycle. Short cycling severely impacts that system's efficiency and equipment lifespan. You also have heat pump equipment types. So depending on the application, the type of heat pump may impact a system's efficiency. So for example, a ground source heat pump will likely have a higher efficiency compared to an air source heat pump due to very stable ground temperatures versus very unstable outside air temperatures. Next, we have heat pump maintenance and operation. So proper temperature settings are very critical for efficient heat pump operation to prevent excessive cycling and energy use. If the heat pump is installed at your facility, ensure your maintenance staff is trained on the proper maintenance and operation requirements, and also the system's design parameters. Okay. So some examples of proper operation and maintenance may include correct thermostat settings based on that system's design for heating and cooling, coil and filter cleaning, regularly checking your refrigerant charge, and ensuring proper airflow. In addition to that, heat pumps are meant to operate at a more stable pace as opposed to something like a residential furnace that may cycle on and off very often. So, large space temperature setbacks or setups are not to be implemented during building unoccupied hours because the system is typically not sized or designed to recover from those large setbacks or setups. A modest setback of 2 to 3 degrees can be considered depending on the application. So just to reiterate that, say for example, your facility is only occupied Monday through Friday, and you have traditional HVAC equipment where on a day like today, you may have your thermostat set at 75 degrees. And then once Friday afternoon comes along, that building is no longer occupied for the weekend. You may increase that temperature set point to 80 to 85 degrees, just to relieve some of that load on your HVAC equipment during those unoccupied hours. You do not want to do these setback or setups with heat pumps, okay? And if you do want to implement a modest setback of 2 to 3 degrees, that should be something you would want to mention, during the equipment design to make sure that it is designed for that application. And lastly, we have modern compressor and refrigerant technology. So newer heat pump models may utilize a variable speed technology for fan and compressor operation to increase that system's efficiency. So variable speed technology kind of does as its name states. So if you have a fan motor, a variable speed technology that can reduce the fan motor speed to save energy during partial load hours. In addition, modern refrigerants may increase a system's efficiency as well when compared to refrigerant used in older models. So for example, R22, that is an older, very common refrigerant, very effective with regard to efficiency, but it causes harm to our ozone layer and produces greenhouse gases. Whereas modern refrigerants like R410A or R32 are indeed ozone friendly. And in addition to that, they are more efficient. So we like to call that a win-win in this industry, and you don't get too many of those. So moving on. So next we will compare some heat pump options. So this table provides a general trends of various heat pump types. This table should be used for quick comparisons and analysis. But if you are designing a system, you would obviously want to do some more in-depth research. So you can notice some trends here on this table. So starting with efficiency, as we move from left to right, from your air source heat pump, dual fuel heat pump, over to your ground source and water source heat pumps, that efficiency increases. That reason, as I mentioned previously, when you're comparing outside air temperature for an air source heat pump as that heat exchange mechanism, when you compare that to ground source or water source, you're likely going to be dealing with much more stable ground temperatures or stable groundwater temperatures. So that will increase your system's efficiency. Installation costs, you can see the trend here. You kind of move from lower to higher installation costs. Ground source heat pumps, they require drilling into the ground and installation of your ground source loop. That comes with a high installation price tag. And then in addition, water source heat pumps, they have more components typically, so that just comes with a higher price tag compared to an air source heat pump. Now, regarding operating costs, that kind of gets flipped around. So with your air source heat pump, you're dealing with that unstable outside air temperature, which may lead to going from partial load to full load. So that just puts more wear and tear on the equipment. And as you can see, for longevity, your air source heat pump is typically less than your dual fuel ground source or water source heat pumps. So next, space requirement. Your air source heat pump will typically take up the least amount of space. Dual fuel heat pumps, kind of the same deal, but that dual fuel component of it, that can be a backup furnace or a boiler. So with more equipment, just requires a little bit more space. Now for those ground source heat pumps, your main space requirement will be that ground loop, right? So if you have a large field next to your facility, that may be a great opportunity to install a ground source heat pump. Or another example may be you have a large parking lot adjacent to your facility, and maybe that'll need to be repaved in the next few years, and you got to tear up all that concrete. That may be a great time to install a ground source heat pump system under that parking lot. Okay. So these are things to consider when you're doing other infrastructure projects as well. And then lastly, space requirement for water source heat pumps. Typically, you need proximity to a water source, whether that be a pond, a lake, a well, or a groundwater source. But also you can have that cooling tower system or boiler system as your water heat transfer mechanism. So it kind of depends with water source heat pumps on the specific type of water source heat pump you're installing. Moving on to climate suitability. So an air source heat pump is best for mild climates. Dual fuel heat pumps work in all climates, but if you're in a warmer climate, you may not need that dual fuel furnace backup. I'm imagining that most of us are in Michigan, um, where that dual fuel heat pump definitely comes into play during that winter period. So keep that in mind. Ground source heat pumps, they work in most climates. Your biggest issue with ground source heat pumps is that ground soil that you're dealing with. And I'll go into more detail about that in a little bit. Maintenance needs. So for your air source heat pumps, typically there's a moderate amount of maintenance. And with your ground source and water source heat pumps, a little bit less. I touched on longevity and environmental impact. So your air source heat pump may have a moderate environmental impact. And then with that furnace backup, that's where the environmental impact gets a little bit worse when you're burning fossil fuels for that supplemental heating. And then ground source and water source are definitely your lowest environmental impacts. So best commercial uses, these are just guidelines. Many of these systems can be applied in wide varieties of commercial facilities, but your air source heat pumps typically found in office buildings, retail spaces, dual fuel in industrial facilities, larger commercial buildings. And then ground source heat pumps are very common for hospitals, schools, and large commercial complexes. And water source heat pumps, commonly found in hotels, resorts, and buildings near water sources. So, moving on, going back to our heat pump efficiency metrics. So, your coefficient of performance, as a reminder, this is your heat produced in BTU per hour divided by your equivalent electric input energy, also in BTU hour or kilowatt hours. This is useful for comparing geothermal heat pump options. This is because of their tendency to have a higher COP value from that stable ground temperature heat source. Okay. Your EER, just a reminder, this is your cooling heat divided by your electrical power input. And this measure is cooling efficiency at a specific temperature. So this makes this value particularly relevant when assessing heat pump performance in consistently hot environments. So not very applicable here in Michigan, but it can be useful in other southern states. Heating seasonal performance factor. So just a reminder, that is your heat produced during the season divided by your electrical power consumed during that season. So this is useful for evaluating heating efficiency over an entire heating season, right? So for colder climates, this metric is crucial for comparing options because it's determining how effectively a heat pump can provide warmth, right? So that's going to be our most common metric used in this part of the US. And then lastly, we have our SEER, seasonal energy efficiency ratio. And just a reminder, that is your cooling output during the season divided by the electrical power consumed during that season. So SEER is useful for evaluating cooling efficiency over an entire cooling season. And this metric is better for comparing options where cooling performance is the priority. Again, in those southern states like Florida or Texas. So we also need to compare heat pump options. So I'm just going to run through some heat pump options and provide some examples where these specific options may be useful. So the first is a very interesting one. It is called variable refrigerant flow systems, or VRF systems. So these deliver precise and energy efficient heating and cooling across multiple zones within a facility. So for example, if you have a traditional rooftop unit, big rooftop unit that's serving multiple zones, and that's reaching the end of its lifespan, a VRF packaged rooftop heat pump system may be a good replacement for that case. So these systems, they have zone comfort. There's typically a single outdoor unit that connects to multiple indoor units, each of which have independent temperature control from a thermostat, and they allow for simultaneous heating and cooling in various zones. You also have variable capacity, which modulates the refrigerant flow based on the demand. And that just allows for a more energy efficient operation. And lastly, you can also have heat recovery, where some VRF systems have the ability to transfer heat from one zone requiring cooling to another zone requiring heating. This also furthers your energy efficiency. And you can see in figure 8, that is one example where you can see that center FCU, it's in cooling mode, and the other two surrounding it are in heating mode. So you can kind of share that heat transfer between different zones for a more efficient operation. So next we have variable speed compressors. These adjust your compressor's output based on demand, reducing energy during those partial load operation. You also have energy recovery ventilators, ERVs, which capture heat from the exhaust air and utilize its energy to precondition incoming fresh air. You also have advanced digital controls. So this would be your smart thermostat or building automation system. These optimize performance and they regulate the equipment operation to meet the facility's needs. You also have DCV or demand controlled ventilation. These systems typically, or these options typically utilize CO2 sensors to adjust ventilation flow rate based on a space's occupancy. So these are ideal for spaces with significant occupant density or significant variance in rates of occupancy at different times. We also have thermal storage systems, which store excess heating or cooling energy for use during peak system demand. And you have solar ready integration, which just enables the system to utilize solar panels for supplemental power or full power. So one example of a thermal storage system application, maybe a facility that has a demand charge or time of day rates based on their bill to shift off during peak load hours. Perfect situation for a thermal storage system, which could help alleviate those additional charges when those thermal storage systems are utilized properly. In addition, an ERV or energy recovery ventilator would be especially useful in a building with high occupancy or a very tight building envelope where ventilation is critical, but the losses can be minimized by having some of that waste heat recovery within your energy recovery ventilator. Sometimes those could be referred to as a heat wheel. It's just a mechanism for capturing that exhaust air to precondition your incoming fresh air. So in summary, unique situations within a facility may provide the right opportunity to utilize specific heat pump options. So just keep that in mind when you're sifting through all of these heat pump options. So next, we will move on to the leading heat pump manufacturers. So this table provides a very general guidance on the current offerings from some of the common heat pump manufacturers in the US. It's encouraged to also do your own research. Manufacturing comparison, the manufacturing industry, it's ever changing, and that goes for their product offerings as well. So these things can change in real time, and always be sure to do your own research as well. And to be clear, Energy Sciences is not for or against any of these manufacturers. We just wanted to provide some general information about current heat pump offerings. So how might you use this table? This could be a good guide for a starting point. So for example, if you're looking to install a retrofit split heat pump system, if you look at this table, Carrier, Lennox, or Rheem may be a good option because they all provide those split system offerings. An alternate option could be a ductless mini split heat pump offered by Mitsubishi Electric, for example. So another example or situation, maybe a large multi-zone rooftop unit nearing replacement I mentioned earlier. This would be a great opportunity to install a VRF system. So if we take a look at this table, Daikin, Carrier, they both offer VRF systems as options. And those would be good to replace for that multi-zone traditional rooftop unit serving multiple zones within a facility. All right, so recommended process for replacement. And how am I doing on time? I'll try to speed it up a little bit, but this is the last section. So it is always advised to hire a trained and certified professional to conduct any HVAC equipment design, installation, or retrofit. Any organization interested in utilizing heat pump equipment in the future are advised to review and or hire help for the following considerations prior to making any heat pump decisions, okay? So we will run through each of these listed here. So first is your climate zone or geographical location. The location of a facility can determine the appropriate heat pump solution. So an air source heat pump or all electric air source heat pump is typically used in mild to moderate climates, the Southeast, Pacific Coast, etc. Ground source heat pumps, as previously mentioned, typically work in all climates, especially cold regions like the Midwest and the Northeast. And as I mentioned, ground soil or bedrock type must be factored into the consideration. So as previously mentioned, as your outdoor temperature drops, the heat pump efficiency decreases. So for locations with moderate to extreme winters, with consistent outside air temperatures below 20 degrees Fahrenheit, Michigan would be a great example of that. A traditional all-electric heat pump may not be a viable option, depending on the application. Rather, a dual fuel or cold climate heat pump may be more suitable. Okay. For those ground source heat pumps, the thermal conductivity of the ground is dependent on the soil type and moisture content. So with that said, a dry, sandy, rocky soil will have a lower thermal conductivity, or rather lower rate of heat transfer. So the presence of bedrock may impact the type of geothermal loop that can be installed. If you have shallow bedrock that's maybe less than 5 feet from the surface, that can make it almost impossible to install a horizontal loop installation. But interestingly, some types of bedrock like granite and limestone, they can actually have a higher thermal conductivity, but those will also likely come with higher installation costs for drilling. So in general, moist, deep soils make for a cheaper and easier install, whereas shallow bedrock or dry soils generally implies more drilling and higher costs. So moving on, water source heat pumps. These are typically found in moderate climates with direct access to that consistent water source. And you have dual fuel and cold climate heat pumps, which are typically found in cold climates where backup supplemental heating is needed. So it should be noted that climate zone maps can give you a general idea, as shown here in Figure 9. They can give you a general idea of how your equipment may operate in your region. But you should always consider local heating degree days and cooling degree days, and those should be utilized when designing any HVAC equipment. There are no rules of thumb when it comes to designing HVAC equipment. So heating degree days and cooling degree days, they are a measurement designed to quantify the heating or cooling demand for a facility based on its specific location. So specifically, heating degree days are derived from the number of degrees that a day's average temperature is below 65 degrees Fahrenheit. Conversely, cooling degree days are derived from the number of degree days that a day's average temperature is above 65 degrees Fahrenheit. And lastly, just always keep in mind that efficiency does not always imply effective operation. For example, an air source heat pump with a high COP does not imply that it'll be effective in your application. And I know I'm running short on time here, but I'll try to wrap it up as quick as I can. We've got a few more slides here. So cost and utility bill impact. Typically, the installation of the heat pump equipment will come at higher upfront costs, but lower utility bills. Not always the case, though. So due to slow adoption of heat pump equipment in this region of the US, this equipment will likely come with a higher price tag than typical HVAC systems. But as the US heat pump market grows, these costs will continue to decrease and stabilize. So further costs may be incurred depending on the complexity of the system. For example, ground source heat pump or VRF system. So some bells and whistles, they may not be necessary, whereas others may make or break the effectiveness of your system. So for example, an air source heat pump equipped with a defrost cycle, that may be very important in colder regions, but simply of no use in southern warmer climates. And also we have emissions impact. So depending on the use and location, heating and cooling needs may make up half of the energy usage within a commercial facility. And electrification of your HVAC equipment is key to reducing carbon emissions. So with your dual fuel heat pumps, you may have a better fit in a colder climate where majority of the electricity is produced from fossil fuels. And that's due to the electrical grid energy generation type. So that should be considered as well. Whereas a cold climate all-electric heat pump may be a better fit in a colder climate where majority of the electricity is produced by renewables. So you take less of a carbon footprint impact there. So next we have building type and function. So understanding key aspects of conditioning such as ventilation needs, peak loads, occupancy schedules, human versus non-human comfort are all imperative to determining a heat pump's suitability. Okay. So consistent space conditioning needs and building occupancy typically deliver the highest operating cost benefits from heat pump equipment. And then buildings that require excessive ventilation or where heating needs are limited may not deliver as high of operating cost benefits. And so we also have equipment availability. So since heat pump systems are considered premium equipment, they may not be readily available off the shelf. It is advised to never replace traditional HVAC equipment with a heat pump system during an emergency replacement. Always take that extra time to flush out all the details, have the right design intent. Just make sure you flush all that out before you're replacing a system with heat pumps. So we also have infrastructure. So you have electrical, physical constraints, and your building envelope. Okay. So electrical constraints, you want to make sure the electrical capacity of your facility can meet this higher electric load, right? So if you have natural gas heating systems and you replace it with an all-electric system, you want to make sure you can meet that additional load. And as previously mentioned, packaged heat pump rooftop units, they're typically a little larger and heavier than your traditional rooftop unit. So you may have to make some structural upgrades such as curb redesigns or retrofits. And then, as mentioned previously, building envelope. An insufficiently sealed and insulated facility will seriously undermine the efficiency and performance of heat pump systems. So we have contractor availability and knowledge. So proper installation, commissioning, maintenance, and operation of heat pump systems are crucial in maximizing the performance of energy in a system. So with limited availability of knowledgeable contractors in installing heat pump equipment, it's crucial to share our success stories and lean on our network, like the 2030 district, to refer the right team for your job. Whether opting to use in-house staff or contract external workforces, choosing a contractor well-versed in heat pump equipment is key to avoid a risk tax, which contractors may hedge their perceived risk associated with heat pump installation and charge more to install them. So you want to try to avoid that where you can. Also, you have incentive and rebate opportunities, and I've provided a link here from the Department of Energy. That's a collection of government and utility rebate opportunities. I'm not sure how often they update it, but that could be a useful resource as well. And lastly, maybe the two most important, I would say, are life cycle cost analysis. This is a compilation of all associated costs and specified project or total cost of ownership, including the following components: initial capital costs, operating costs, disposal costs of replaced equipment, residual salvage value of equipment, and inflation. So life cycle cost analysis is a little more in depth than just doing total cost of ownership. It considers the time value of money, right? So $1 today isn't worth the same as $1 tomorrow. So all of that is sort of considered into a life cycle cost analysis. And lastly, energy modeling provides a simulation of a facility's energy usage, typically utilizing hourly weather data over an entire year. So this model input typically includes the following: your building envelope characteristics, internal loads, HVAC system performance, and local weather data. So energy modeling feeds accurate performance data into the life cycle cost analysis software. And this ensures that financial decisions are based on realistic energy use projections. And this integrated approach is especially important for heat pump systems, where you can have significant variance in climate, load profiles, and system design. So with that said, on to the Q&A portion of this presentation. I'm sorry I went a little over, but hopefully we have some time to get some questions answered here. And I just want to say thank you everyone for attending today.
Thank you. That was great. That's probably an excellent resource presentation for us to keep with us. So we do have several questions, and let's see, maybe yeah. So how does this presentation apply to residential systems?
Good question. So I did make this presentation mainly for commercial applications, but pretty much anytime I mention a split system air source heat pump, that can typically be used in a residential application. So those mini split systems, the air source heat pumps, are typically common residential applications as well. So I hope that answered that question.
Okay. Yep. A lot of the efficiency ratings and all of that all apply, no
Yes,
matter
yes,
what
good point. Exactly.
does. Yeah. Yeah. Um, and Erwin, if we don't answer this question completely, maybe you can raise your hand too. What about hot water heat systems with forced air cooling?
So
So,
you
oh,
can
I see. It's a
integrate,
split system, really. Yeah.
yeah, you
Mhm.
can integrate your heat pumps. So typically, the forced air cooling, that'll be your air handling unit. And actually, let me back up. So essentially, sorry, I don't know if you can see my pointer, but the split system on the right-hand side, that unit just below the roof level, that would be your air handling unit, in which you would connect your refrigerant piping to that coil. The heat pump may come with its own coil, it likely would, but that would be installed at the air handling unit. So that's how a heat pump would be integrated into forced air cooling. With regard to hot water heating systems, this would be kind of an applicable system for that, where your water source heat pumps may operate with that supplemental heating from that boiler when needed. So it's kind of a more of a backup with regard to hot water heating systems.
Okay. Thank you. All right. Then the next one was, okay, so what happens, you talked about the drop in efficiency with low temperatures. Well, what happens to the efficiency as the temperatures rise? Like, you're at 95 and
Yeah, so that's a good question.
high humidity.
So in general, as outside air temperature increases, your efficiency will increase, but obviously, yes, there is a cap to that. Um, so
Your efficiency increases as your temperatures go up?
yes, because if in an out air source heat pump, your heat transfer is from the outside air. So with warmer air temperatures, you allow for better and more heat transfer. Um, so yes, that is actually more specifically for heating mode, in which that's the case where there's more heat in the outside air for you to extract. In cooling mode, um, that's a good question. I'll have to do a little bit of research, and Erwin, if you want to email me your question, I can get you a very solid answer on that. Yeah, I focus more so on the heating components of heat pumps today, just because I know most of us are local to Michigan, and that's where it's really important with regard to efficiency is on the heating side of things, not necessarily cooling.
Yeah, because the delta T is so much larger in the
Hmm.
heating cycle. Yeah.
Yep.
You're only looking at maybe a maximum of 20 degrees or maybe 22 degrees that
Yeah.
you're trying to where you're looking at, 70 degrees sometimes in the heating delta T. All right.
Yeah, and I just wanted to quickly mention with regard to the hot water systems. So there are some heat pumps that provide hot water in combination. So they can do domestic hot water. They can utilize heating hot water from a boiler. And you could also potentially integrate solar hot water as well. So
Yeah. And one of the things that we found out with, doing some energy audits with especially food service businesses, if you have a heat pump hot water heater in an area that has a lot of heat gain, equipment, it actually helps to cool the space. And the water heater is more efficient too at the
yes,
same time.
absolutely. Yeah,
So
and
that's
that
a
reminds,
win-win.
yep, very much
Mhm.
so. Yeah, and that reminds me that's kind of more of an industrial application where you are utilizing that waste heat recovery in your
Mhm.
processes. So that's a very good example, Jan. Thank you.
Yeah. All right. Well, thank you. Let me see if there are any other questions here. Let's see. I think that's it. Great. Well, right on the dot. Thank you very much, Zach. And I just want to invite you all. I did put the link in. We're having workshops on HVAC systems, renewables, funding your projects. Um, and the Washtenaw County is going to look at, they just completed their Amoresco survey on their decarbonization strategies for their whole building portfolio. And it's all happening this Thursday afternoon. And you can also join us for some food. So that link is in the chat if anyone wants to register. We still have some room. So while we look forward to this is our last webinar until September. So enjoy your summer. And Zach, thanks again. This has been awesome. Karen, thank you very much for all the behind the scenes work that you do. And we appreciate our collaboration with AIA here in Valley and the Washtenaw Contractors Association. With that, stay cool and enjoy the rest of the summer.
Thank you, everyone.